Okay. I hope you guys are doing good. Today we are going to be doing some fun activities. We will sketch things. So hopefully sketching things gets you a little bit, in a relaxed environment. All we are going to do is we're going to first lay out some rules about how to sketch root locus, and then we'll try to sketch them for a few examples. So what is a root locus? You have certain poles in the S-plane, and as you change system parameters, those poles are going to move around in the S-plane. We are just going to sketch how they move around. So the movement of the poles is being tracked by the root locus. And depending on where they are, we can say, oh yeah, over here, the response is critically damped. Over here, it's underdamped. Here, it's overdamped. Here, it is marginally stable. And all of those ideas that we talked about earlier in the semester based on where the poles are located. So first, we'll talk about root locus, which is to sketch the movement of the poles. Then we need a shortcut. Routh-Hurwitz criteria gives us a shortcut to finding out whether a system is stable or not. So instead of plotting out the root locus, by just looking at certain coefficients of the denominator polynomial, we can actually find out or comment about whether the system is stable or not. We don't have to find the roots, right? So think about it. If you're in your denominator of the transfer function of your system is given, the denominator has a 10th order polynomial. How will you find out whether the system is stable or not? Well, MATLAB is one option, which is essentially you're going to have to find the roots, right? Roots of the 10th order polynomial, then make sure that all the real parts of those roots are negative. But there is the Routh-Hurwitz criteria is essentially a shortcut to that. So without evaluating all the location of the poles, you can still comment about whether it's stable or not. So that's RH criteria. Let's talk about sketching the root locus. And we'll be talking about feedback systems here. And I have two of them. Both of them have the same loop transfer function. So X of S is representing the Laplace transform of my input. H of S is representing what? H of S over here is representing system dynamics. This is too big. Need to go even smaller, sure. So H of S is in Laplace the system dynamics for the forward path. Y of S is output in Laplace domain, which is being fed back through these feedback dynamics. Where the feedback dynamics are some k value, some parameter k that you can manipulate times g of s, some function, some transfer function, as a negative feedback back into your system, right? So that's, you have negative feedback over there. So that's one closed loop system. Over here, if you sort of chop this off, let's suppose that you chop here, right? If you break this, then what do you have? You have X as the input, H is your system, Y as your output. There is nothing in the feedback. And what would be the transfer function for this? It would be Y divided by X, which is simply going to be H of S. If you break it there, right? If you break it here. But what if you break here? If you break here, input is X, it goes through H, goes through K G of S, and you have your output. It is still not closed loop, but this is what we call loop transfer function. So your loop transfer function is X of S going into H of S, going into KG of S, and that's your output. So output divided by input is going to be your loop transfer function. So what is that going to be? KG of S cascaded with H of S. So the product of KG of S, H of S is called the loop transfer function, where essentially what you're doing is when you make it, when you close the loop, you close the loop. When you open the loop, you chop it off over there. So that is one version of loop transfer function being the product of these two guys. But because it is a product of two things, you could also have k over here, and it will give you the same product. X of s, system dynamics of k h of s, output is y of s, being fed back through g of s back into your to close the loop with negative feedback. So even here, the loop transfer function is what? The product of these two guys, right? So imagine this. Imagine this to be something like this: x, too big, x, h, and y. So this is g here, this is k h of s here. Right? Input k, g, y. Input k, g, and then you're breaking it there. So here, in both these cases, this or this, the closed loop transfer function is exactly the same as before. What was that? Forward divided by 1 plus product, right? The thing that we derived in the last class. So forward is h of s divided by 1 plus product. 1 plus product is k h of s g of s. And for this guy, again, it is the same thing. Closed loop transfer function, which we are writing over here, is with negative feedback, forward divided by 1 plus product. Forward is k h of s. 1 plus product is k h of s g of s. So T of s is representing closed loop transfer function. But as I said, open loop transfer function or loop transfer function is going to be only the product of these two guys, which we are writing over here. And we are calling that loop transfer function. So you will see me using the term loop transfer function or open loop transfer function. What I'm referring to that, when I say that, I'm referring to the product of both the transfer functions in my system, both forward and in feedback. Now, if you wanted to talk about stability, what do? You take the closed loop transfer function, you set the denominator equal to 0, and for all the values of s that make the denominator go to 0 will be your poles. And depending on whether they are lying in the right half or the left half or on the geometric axis, then you can talk about marginal stability, stability, unstable behavior, and all of that. Now, closed loop transfer function, closed loop poles. What are closed loop poles? Well, closed loop transfer function will give you closed loop poles. Loop poles and zeros will be for loop transfer function. The zeros and the poles of loop transfer function are going to be called loop poles and zeros. The zeros and the poles of the closed loop transfer function are going to be called closed loop poles and zeros. So when you're talking about when you're talking about the closed loop stability, you are looking at the closed loop poles. But when you talk about the root locus, what you do is you monitor the movement of loop poles and zeros because they are part of this particular characteristic equation. So as you change k, the loops will move around. And you'll find that. We'll try to use that particular denominator equal to 0 condition to see how the poles move as you change k. So when you looked at the closed loop poles, which was denominator of the closed loop transfer function going to 0, so those were your closed loop poles. The condition was this, the characteristic equation. That's your defining equation of the root locus. You will have some values of s when you plug in that will satisfy this equation. And those would be called what? Those would be called closed loop poles. So now with this, you can actually have a question so far? So for now, here are the things that I'm expecting you guys to sort of get. One, what is a closed loop transfer function? Two, what is a loop transfer function? Right? The second one is, what are the closed loop poles and what are the loop poles and zeros? Next, what is the characteristic equation of the root locus? So far, and that characteristic equation is coming off of the closed loop transfer function, which is the actual system. But it has the loop transfer function embedded in it. Now, when you look at this particular statement here, 1 plus k h of s g of s equals 0, you can write two statements based off of that, one based on the magnitude and the other based on the angle criteria. magnitude value is, from here, you rearrange. You write k h of s g of s to be -1. Then take the magnitude on both sides. What do you get? Magnitude of the left-hand side should equal 1. Now, with this, you can find k as 1 over magnitude of h of s g of s. So this is telling me that if the denominator has to go to 0 for a certain value of s, I can use magnitude criteria to find out the corresponding value of k. That will make the denominator go to 0. So I can actually use this to find values of k that will satisfy that particular equation for a certain value of s. But I still need to find out what that certain value of s is. And the angle criteria will help me do that. So magnitude criteria is helpful in finding values of k. However, the angle criteria will help us sketch the root locus. Let's take a look. K h of s g of s had to equal -1. What that means is the phase of k h of s g of s should be an odd integer of pi, right? -1 pi, -2 pi, plus 3 pi, and so on. So when n is odd, right, you're going 1 pi or 3 pi or -pi. You're landing at -1. So the angle criteria over there says for a value of k multiplied by h of s, which is your system dynamics, the forward path, g of s, which is your feedback path. When you multiply, find the phase of that. If that phase is a negative odd multiple or odd multiple of pi, then it satisfies this root locus. That means that it is going to be on that particular path of how the poles move. And then what is the value of k over there? Well, you use the magnitude criteria to find that. So far, we have only laid out two criteria that are going to define our root locus. I'm hoping that when you start seeing examples of certain k, h of s, g of s products, you will start seeing that root locus develop. What I want to say is, as long as we are going to form certain rules for these sketching of root locus, and as long as you are following the rules, you will be able to get the correct sketch. Next, open loop transfer function or loop transfer function is this k h of s g of s, which is what we have seen earlier. Just the product of things that are in the system dynamics and the forward dynamics, feedback dynamics. Questions about magnitude criteria and the angle criteria? One is going to be used to sketch the root locus. The other is going to be we are going to use the magnitude value to find the k corresponding to any point in the root locus. Next, simple exercise here. And if you get this, you will get everything else that follows after this. We have simple system here. It's a feedback system. Input in the S domain is x of s. We have a negative feedback going on. System dynamics are h of s, which is a function in s, 1 divided by s times s plus 2. Next, there's a feedback. In the feedback path, there is nothing but a k. So k is just some parameter, some gain value that we have in the feedback path. Now, with this, you can find out the closed loop transfer function. You can find out the loop transfer function. You can find out the characteristic equation. We can do all of that. So, for example, what would be the loop transfer function? Loop transfer function would simply be the product of this guy with this guy, right? It would be k divided by s times s plus 2. That would be your loop transfer function. What about closed loop transfer function? It would be forward divided by 1 plus product. So h divided by 1 plus kh, right? That would be a closed loop transfer function. What is the defining equation of the root locus? 1 plus k h of s should equal 0. There is no g of s involved here. So 1 plus k h of s should go to 0. That will be your defining equation. 1 plus k h of s goes to 0. We know h of s. K is some arbitrary value. Fill in h of s in the characteristic equation. Simplify. What you get is a quadratic in s. That's your defining equation of the root locus. And you can clearly see that there are going to be two roots for S. It's a quadratic, and both the roots are going to be dependent on K. So from this, I'm pretty sure you guys are able to go here, right? Negative B plus or minus B squared minus 4AC by 2A. You guys know that formula. You use that, you find out the values of the two values of S. Essentially, those are your poles, the starting poles, because it depends on K. As I change K, the poles are going to move. So let's see. Let's try to take a look at some values that are going to be. When K is 0, what happens there? When K is 0, plug in K equals 0 here. What do you have? Negative 1 plus 1, 0, right? So when K is 0, you get this particular point. Yeah, that's where your pole is when K is 0. And as you're increasing K, as you're increasing amount of feedback, what is happening to the pole locations? You increase K to 1, 2, 3, 4, so on up to infinity, right? How are the poles moving? Well, when you have K equals 0, actually you get two of them, right? All right, so this is 0. You get minus 1 plus or minus 1. So you get 0 as well as 2, negative 2. You get this guy as well. So you get two poles there. That's when K is 0. As you're increasing K, what is happening to the poles? I've just written down a few values here. When K is 0.5, the poles move there. 1, they both are coincident at negative 1. When K is 2, they become complex conjugates of each other. And when K is 5, the poles are actually traveling up, but both are complex conjugates of each other. If you try to plot these out in the S-plane, take a look. This guy moved here first, this guy moved here first. They both met over here when the system was critically damped. And when you increased K even further, one pole moved up here, the other pole moved here. What was the state of the system then? The system state was under-damped system. So it went from an over-damped system to a critically damped system to an under-damped system as you are increasing K. What if you increase K to infinity? What happens then? Well, it will keep going up over here. It will keep going up over here. It will keep going down over there. And the green path is the root locus. So let me ask you this. Where is the root locus starting? At a pole. The root locus starts at poles. Where does it end? We don't have a 0 over here, right? We don't have a 0 here. But if we did, you would see that it actually starts at a pole and ends at a 0. But over here, because we don't have a 0, our 0 is at infinity. So it is going to a 0 at infinity there, and it is going to a 0 at infinity over here. Because we don't have a 0. It's like having a 0 at infinity. How is the root locus being tracked? You are changing the value of K from 0 to infinity. So as you change the value of K from 0 to infinity, you are actually controlling how much negative feedback you are applying to this system. As you can see, if K is infinity, what happens then? You are applying all of the feedback, right? You're applying a lot of feedback to the system. What that means is your response output will go to 0 then. So that's why I say, as you're changing K from 0 to infinity, you are moving from poles to zeros in the system. Because when K is infinity, you are providing all of it as the feedback. Which means, what is that? X minus infinity, right? You have nothing at the output. All right, now let's take a look at validating that our root locus that we sketched over here actually satisfies both the criteria. What is that? Magnitude as well as angle. For the angle, what did we say? We said the angle of k h of s g of s has to be an odd multiple of pi. If you are on the root locus, then you satisfy the angle criteria. So let's take a look. So for this, what I'll do is I will make some test columns. This is just to check. This is not going to be part of our sketching root locus rules. This is just to illustrate that the angle criteria works. So I'm going to take some test columns here. My first test column is going to be here, the j omega axis. My second test column is going to be here. My third test column can be here. Fourth test column can be here. Fifth test column can be here. Right? I'm talking about test columns, and I'll pick points on these test columns and check whether they satisfy the angle criteria or not. And we know nothing on this will satisfy. Everything over here will satisfy. Nothing over here will satisfy. Right? Because that's what we claimed over here. Right? Only column test column 1 highlighted in blue, only that should satisfy. That's on the root locus. So everything on that blue line should satisfy. Let's take a look. Our first column test point that we highlighted in green, that was the j omega axis. On the j omega axis, what is the value of s? Well, I have 5 points that I'm considering over there. Plus 1j, plus 2j, minus 1j, minus 2j. These 4 points are being substituted in the angle. This is literally angle k, h of s, g of s, and you are checking whether this is an odd multiple of pi or not, when n is odd, right? And because g of s in our example is 1, we literally are checking for k h of s. H of s is given, 1 divided by s times s plus 2. So if you put in this point, negative 2j, where is this guy? So let me just, this blue, negative s, s is negative j2. Where is that? On the first test column. It's right here. Right? Plug that in. All right? Instead of s. You got 1 divided by negative 2j, negative 2j plus 2. Multiply, find the angle of that complex number. You will see that it will evaluate to 135. Not an odd multiple of pi, which means this failed the angle criteria, which is to say it should not belong to the root locus, and it doesn't. It's not on the root locus, right? Root locus is over here. Similarly, you put in points over here, negative 1j, 1j, 2j, you will see that they will not satisfy the angle criteria. But when you move to test column 2, you put in, what are these values? Can somebody tell me what this value is for s? On the real part, you have negative 1. On the imaginary part, you have negative j2, right? And similarly, you know what that s is. Negative 1, negative j1, right? And so on. So when you put these test points into the angle criteria and evaluate the angle, you will see that they will all satisfy. You will get odd multiples of pi. Where are we doing that? We are doing that over here. Second column test point. Put in the 5 values of s, evaluate the angles. You will see that you either get 180 or negative 180, or you could have gotten higher odd multiples of 180 as well. No matter what, you are getting an odd multiple of pi, which satisfies the angle criteria, which means that these 5 points belong to the root locus. Question so far? We are just picking some arbitrary points. We could have picked other points as well. Now, let me ask you a different question. The claim over here is, at that particular point in the S plane, k is 5. So as you increased k from 0 to infinity, right, when k became 1, you came here. As you increased k even further, 2, it came here, 5, it came here. But how do you check whether, in fact, when S is this, k is 5? Which criteria can you use to find k? Magnitude criteria, right? So all you would have to do is k equals 1 divided by magnitude of h of s, g of s, right? When the s, evaluate that for a particular s. So in our case, let us evaluate that for negative 1, negative j2. What is this? g of s is 1, so there's nothing there. You only have 1 divided by h of s, which is s times s plus 2. Evaluate that for s equals -1, -j2, and find the magnitude as well. Put the number in there, simplify, find the magnitude, you will see that it will come out to be a 5. Right? So for any point in the root locus in the S-plane, you will be able to find what is the value of k here. Right? So when you are looking for the value of k there, you use magnitude criteria. To check whether it is part of the root locus or not, you use the angle criteria. In fact, we are going to use the angle criteria to formulate all the rules that are going to be used to sketch the root locus. Questions here? All right, let me just continue with this. It's now going to be pretty simple to prove this. First test column, nothing satisfied. Second test column, all the 5 points satisfied. Third test column, this is, as we are working our way to the left. Nothing satisfied there, nothing satisfied there. So the only 5 points that satisfied our angle criteria were in our second test column, right here in the blue. Nothing else satisfied. If you are curious, you could pick any point here and check. You will see that the angle criteria will satisfy for that. So if you put S as any real value between 0 and -1, or between -1 and -2, you use that particular S, but real, put that in the angle criteria, you will see that you will get an odd multiple of pi. So if you're curious and you want to check it out, you can do that. So when you now start plotting things, you had these test columns, test column 1, test column 2, test column 3, test column 4. And if you put out all the angles, you don't have to do this. This is just for explaining purposes. You put out all the angles that they gave you. These 5 points gave you 180 or -180 or odd multiples of pi. Every other thing over here gave you something else. So those are not part of the root locus. Only these points are part of the root locus. And like I said, you can find the corresponding k value for any point in the S-plane, say S0. If you want to find the corresponding k value, how much should I? So here, you can find this out, right? You can say, what should I set my k value in this particular feedback system so that I get a critically damped system? Right? So then you say, all right, critically damped system means I should get 2 poles over here. So I'm looking for what that k value is. Take your magnitude criteria, put the value of s in that as -1, find out the k value. You will see that you will get, I think, 1 in this case. Yeah, you will get a 1 there. So using the magnitude criteria, you can find out what the k values are at those points. And over here, we have just done it for the 5 points that satisfied our angle criteria. So these are on the root locus. We found out their k values. We started with 0. Over here it was 2, then 5 at the end. So again, kind of maps the same here, right? Started at 0 over here, 1, they both met over here, then 2, they were here, complex conjugates, and 5, it became underdamped, right? So it went from overdamped to critically damped to underdamped system. And you know the characteristics, right? Slow decay, no oscillations. Fast decay, no oscillations. Oscillations are there. Like now you are able to control that k to control the system stability behavior. Questions? Straightforward? All right. Let us talk about the rules now. So based on the angle criteria, we are going to formulate the rules. Now, some of these are going to be sort of without a proof. But what we are going to do is, we are going to use these rules to sketch any root locus. So you tell me what the system is, tell me system dynamics, tell me feedback dynamics, and I will show you the root locus. And if I know the root locus, then I also know, pick any point, I'll tell you what that k value is. No, now, the root locus, where does it start, where does it end? So that's rule number 1. Rule number 1 is, the root locus always starts at poles. Poles of what? poles of the loop transfer function, right? This is for the loop transfer function. Because remember, we are looking for 1 plus loop transfer function equals 0, right? That was our characteristic equation. So we are looking for the poles of the loop transfer function. That's where the root locus will start. And at those points, k is 0. And as you increase k to infinity, you will be moving from a pole in the system to a 0 in the system. So root locus will start at a pole and end at a 0. What if there is no 0? That means that you are ending at a 0 at infinity. So it's like going up into infinity. And in any direction, vertically or horizontally or any direction, you're just not ending. But if you have a real 0, I shouldn't say real 0, a finite 0, then it will end there. Next, second rule is, if you are looking at root locus on the real axis, then the root locus alternates as you are moving from right to left. You see this? I can apply it over here. Just observe the real axis. If you just observe the real axis, what do you have? No, yes, no. No, there is no root locus here. Yes, there is root locus here. No, there is no root locus here. You just alternate. And on what basis? Poles will be defining the boundaries. Zeros will also define the boundaries. Right now, there are no zeros, so you don't see that. But at least on the real axis, it is so easy to find out whether there is root locus or not. You just alternate. Start from here, move left, no, yes, no, yes, no, yes. Right? So in this validates, right? This checks out. There is over here, nothing here on the real axis, nothing here on the real axis. So the second rule is only meant for real axis, nothing on the other part. So on the real axis, the root locus alternates on the real axis. No, yes, no, yes, no, yes. Questions about these two rules? Hopefully with some examples, it'll get even better. So these are 3 examples on this slide, and we are only interested in the root locus on the real axis. We are not observing other aspects of the real axis. So here, what is happening here? You have, this is loop transfer function or open loop transfer function, k, g of s, h of s. It is given to us as a transfer function which has 3 zeros and 3 poles. Where are the zeros? You have zeros at s, -3 and -4. So those are here, here, and here. And you have 3 poles. Where are the poles? Maybe use pink. 1, -1, -2. There, and there. Yeah? Now, if you start all the way to the right and alternate no, yes, no, yes, so you've got no, yes, no, yes, no, yes, no. Now, this is only for the real axis. But if you now combine it with rule number 1, you know that the root locus starts at a pole, ends at a 0, right? So you see, all right, started here, ended here, all right, that's it. It went from here to here as you increased k from 0 to infinity. So as you increase k, this guy moved from here to here. Next, what do you do here? It has to start, so you know that there is root locus here, you know that there is root locus here, and you know that it starts at a pole and ends at a 0. So can you guys tell me, just as a guess maybe, what do you think happens here? How can you find something that starts at a pole and ends at a 0 here? Yeah, so you have to go away, right? Like you have to go away from the real axis here. You guys see that? So let me use a different color here. Maybe I use green. Maybe I bold it. So this guy moves here. Yeah, this guy moves here as you increase k. At some point they meet. Maybe in the middle, maybe not be in the middle. At some point they meet on the real axis and they break away from the real axis. They break away from the real axis. In some angles, they break away. You keep increasing k. They break in to the real axis at some point, eventually ending at a 0. So you see what happens. They start at a pole, ends at a 0. As you increased k over here was a 0 for both of them. As you increased k, they came in together, they break away from the real axis, go around, break in to the real axis, and then end at zeros. So there is a breakaway point, there is a break-in point. Breakaway point is right here, break-in point is right here. But our goal was not to fill in all the details. Our goal was just to figure out whether things, is the root locus on the real axis or not? And we answered that by using that no, yes, alternating behavior. Questions about this example? Maybe I'll leave it here. Maybe, yeah, all right, I'll leave it like this. Now, unless you are using a computer program, you are not going to know exactly how this went, right? Some student may draw it like this. Some student might draw it like this. There's no way to know exactly what trajectory this took until you actually use a computer program or you plug in, all the values of k and take a look at how it moves. So in our homework or exam problems, you don't have to be like exact what shape it is. There's no way to find out. But what you can do is show that there is a break away from the real axis and there is a break in later. Now, quick question. Let's say that the k value over here, the k value is k1. And over here, the k value is k2. Which one is big? Which one is greater? Which one? K2 is greater. Starts at when k is 0. As you're increasing k to infinity, that's how the root locus is moving, right? So it was actually 0, close to 0 here, right? Maybe 1, maybe half. And then even if you moved it, as you increased it even further, that's when you got k2. So over here, the k corresponding to the breakaway point was much smaller than the k that corresponds to the break-in point. Good. Oh, over here? This guy? 0 to 1. Oh, right here. Oh, yeah. So k is 0 here. As you increase to infinity, k is infinity here. So as you're doing all of this, that guy is only moving this much, right? So for all of them, when they're poles, k is 0. As you increased k, this guy was so slow in moving here, while all of these, they did all of that. So there's no way to know rate at which those poles are moving, but we know the trajectory. Other, wait. Yeah. Nothing. We already know it's no, yes, right? So we already know nothing is there. Root locus. Yeah, there's no root locus there. Between -2 and -3, nothing there. On the real axis, it is nothing. But in the complex plane, there is.
So would there be any?
-1 to 0. No, because it has to start at a pole and it has to end at a 0. There are 3 zeros. So they all have to have an ending point. Right? So I need to start here and I need to end here. The only way I can do that is if I did this, right? I don't know if I go here and I come back, but I have to come back to that 0. You see that? So that exact movement could be this or could be this. I don't know until I plot it, but I know that it has to break away from the real axis and it has to break in later. Yes. So this to this, right? This to this, direct match. From here, there's no way. Like as I increase k, there's no one-to-way mapping. There's no one-to-way one. Like I know this one is yeah, one-to-one, but over here is just movement of the poles. They are not say distinct poles, right? Like it could. It's just a movement of the poles. It has to end at 0. Oh yeah, like there's no way to know. See, when they break away, there's no distinguishing between them once they meet, right? Like once they are over here, they are both are at -1. That's it. They are identical. They are two roots at -1. So they have lost their. No, there's no way. So only for this, you know, this is going here. Yes, you know it's going there. Because I have to be on the real axis there. You now, so here you have to use your previous rules, right? So it's like a puzzle, and you have to use pieces from the previous rules to piece it together. So suppose, okay, so let's take a hypothetical. If this guy was going here, how can you have a root locus on this? Right? Like I need a root locus here, right? Because no yes on the real axis. But I cannot have any root locus here. Hold on. I have to start here, right? And I have to be here.
Okay, I see.
That's it. I have ended. No. They are matched, but they lose their distinguishing nature once they meet. So one pole has to end at 1, 0. That 0 could be finite or it could be at infinity. So if there are no zeros, that is like going to the infinity. Good. For any point which is on the root locus, you can use the magnitude criteria to find the k value. Absolutely. Yeah. As long as it's on the root locus. Yeah. Different amount, always possible. So infinity, right? Like over here, we didn't have any 0. We didn't have any 0 here. There it is. Right. All right. Let's move on to. All right. I think you guys are having fun now. What if on the real axis, we are continuing with our on the real axis behavior. What if you have two coincident roots? So we have two coincident zeros and we have two coincident poles. So when you have something like this, right, two poles here, two zeros here, you actually have to sort of think about it with some small distance separation between the two poles. So you actually go no, yes, no, yes, no. So right away you know that there is a yes there, there is a yes there. So how about what happens, you know, it has to start at a 0 and at a pole, right? So you'll go end, right? So something similar to this. Next, what if you have 3 poles but no zeros? So when you have 3 poles and no zeros, you have something like this. 3 poles, they're all coincident at -1. So again, you have to imagine them slightly separate from each other, something like this. There are 3 poles. So you go no here, yes, no here, yes. You see that? So on the real axis, we were able to find out. Now tell me, what is going to happen here and what is going to happen here? There's no 0, right? So these 2 guys will need to come up like that, and then it will shoot away up and down, right? Going to infinity, 0s at infinity. How about this guy? Go to the left to a 0 at infinity. You see that? So this guy moves this way, this guy come together, break away, go to infinity. So when you put it together, piece it together, you will see that there's one going left, and then you're going one here, one here. But we are not observing things apart from the real axis. For this slide, we are just looking at things on the real axis. So it'll look like this, moving left. Questions here? On the real axis should be straightforward, right? No, yes, done. So what are you doing? Let's just try to start developing a strategy here. Given a loop transfer function, first I will mark my poles and zeros. Then I will mark my root locus on the real axis. Then I will start using my other criteria, right? Go ahead. Yeah, so you just try to visualize them with some separation and then apply no, yes, no, yes. All right, next. Third rule, root locus enters or exits multiple poles and zeros at equal angles. So suppose over here, we had multiple poles here, multiple zeros over here, multiple poles over here. So when you have multiple coincident poles or zeros, poles for exiting, zeros for entering, what you have is the root locus enters or exits at equal angles. So for example, here at the first one, we have 2 poles, both of them are at -1 right here. The root locus exits here. At what degrees? Equal angles. What are the angles? Pi divided by n, pi divided by 2. So you got plus pi over 2 and negative pi over 2. Those are the angles at which the root locus exits. How about enters? There's no entering here. There's no 0 here, right? There's no 0 here. So it doesn't enter. Next, n equals 3. So you have 3 poles. They are all coincident at -1. They are going to exit out of a pole at what angles? Pi divided by 3. So you have one guy going at 60, one guy going at 180, and then you have another guy going at -60. All at equal angles, exiting from a pole. Again, no zeros involved here. But if you had 3 zeros, say if you had s plus 1 cubed, root locus would be entering to that poles at equal angles. Again, pi over 3. Last one, n equals 4. How does because you see, it has to start at a pole, right? And it has to exit out of a pole. Now, because there are 4 poles, you need to draw 4 lines out. And now we know the angles at which they go out. It's going to be pi over 4. So it depends on the number of poles. They are split in equal angles. Again, no proof over here, but a rule that determines the root locus. Another note here is there is always symmetry about the real axis. You see, symmetry about the real axis here, symmetry about the real axis here, symmetry about the real axis here. So for root locus, there will be symmetry about the real axis. Not true for vertical, only for horizontal axis, the real axis. Next, a few parameters for the root locus that we need to compute, which will actually help us sort of determine the guiding lines for the root locus. One is pole 0 excess, PZE, and the other is number of asymptotes, which is nothing but pole 0 excess. So find the number of poles, find the number of zeros, subtract them, you get pole 0 excess. So pole 0 excess is number of finite open loop poles minus number of finite open loop zeros. So for example, if you have a loop transfer function that is given to you here, which is k s plus 1 divided by s squared times s plus 3, How many poles do you have? How many zeros do you have? Well, you have 2 zeros at 0, two poles at 0, and another pole at -3, and you have 1 0 at -1. So you have 3 poles, 1 0, 3 poles, 1 0. Subtract them, you have 2 as your pole 0 axis. And these are only for finite poles and zeros. Next, pole 0 axis, that simple calculation is actually going to tell you how many asymptotes are you going to have. Asymptote is essentially a guiding path for the root locus. So I typically draw it as a dashed line, and I use that as a sort of guiding lines for my root locus. And I'll show you guys that with an example. So asymptote is a straight line to infinity that is a branch of the root locus tends towards, a guiding path for the root locus. So how many asymptotes are you going to have? Exactly the same as pole 0 axis. Next, asymptote angle. So when you're drawing that guiding line, at what angle is it going to be, and where is it going to be located? So you know the number of asymptotes. You also need to know two more things about the asymptotes. One is at what angles are the asymptotes. The other is where is the location of the asymptote. So asymptote location, asymptote angles. Asymptote angle, AA, not to be confused with the other A, is, no, didn't land. All right, fine. Oh my gosh, you guys are so nice. Negative pi times m divided by PZE. We know PZE from before. M is some odd integer, and negative pi. So if you know PZE, then you know asymptote angles. Well, m is odd, so is there a limitation? Well, you only consider all the unique values of asymptote angles that you can get. So let's take a look at some examples here. Loop transfer function is given, k divided by s plus 1. One pole, no zero, pole 0 axis is 1. So if your pole 0 axis is 1, what is the asymptote angle? Negative pi m divided by PZE. So in this case, it will be negative pi m divided by 1. Well, m can be 1, -1, 3, -3, plus or minus 5, plus or minus 7. But no matter what, you only have one angle, right? Which is pi. So you have only one angle there, pi. So asymptote, which is sort of an imaginary line, which is going to guide the root locus, is going to be at an angle negative pi. And you see, with one pole, it is guiding the root locus, right? It is on the root locus. Because it starts at a pole, ends at a 0, there's no 0, so it's going to infinity. No yes, so no, nothing here, yes here. Yeah? Next, you have k divided by s plus 1 squared. Pole 0 axis is 2. There are two poles, both of them at -1, right here. We know that from the equal angle criteria for exiting, the root locus exits at plus or minus pi over 2. What about the asymptote angles? Asymptote angles using the formula over here, which is negative pi m PZE. Negative pi m PZE is 2. You just plug in m -1, 1, -3. You just try to find out only the unique values of angles that you get. You will see that there are only two unique values that you get, pi over 2 and 3 pi over 2, which is right here and right here. So these are two cases where the asymptotes are sort of lining up with the root locus itself. Next, you have 3 poles, no 0. Pole 0 axis is 3. Asymptote angles are obtained by the same formula here. You get pi over 3, negative pi over 3, and pi. So those are your guiding lines for the root locus. And in this case, again, because you have 3 poles, no 0, all the poles are at -1, it just so happens that the asymptote lines and the root locus are on top of each other. That's generally not the case. It just so happens over here. Questions about asymptote angles? Straight lines that work as guiding lines for my root locus. I know how many lines are going to be there using number of asymptotes, which is PZE, and I now know at what angles they are going to be, asymptote angles. Next, I also need to find out the location, right? What is the location of my asymptotes? I know the angles, I know how many number of lines, I need to find the location. So for the location of the asymptotes, I use this particular formula here. Summation of all the open loop or loop pole locations minus summation of all the loop zero locations divided by PZE, pole zero axis. So let's try to find out the asymptote location for this particular example over here. You are given a loop transfer function. You have no zeros. You have 3 poles. So right away, you know that pole zero axis is 3. Next, what are the locations for? So let's try to find out this one. Let's try to find summation of the open loop pole locations. What do you have? 0, -2, -4. So when you add up 0, -2, -4, you get the summation of open loop pole locations. Of course, there is no 0, so this term goes away. And then in the denominator, you have 3. So asymptote location works out to be -2 in this case. Now, what we know is asymptotes equals PZE. So we know that there are going to be 3 lines, 3 asymptotes. Angles are going to be plus and minus 60 and 180 because negative pi m divided by PZE, that evaluates to be 3 angles. What is the location? -2. How do you sketch that? Location is at -2. One guiding line going at 60, the other guiding line going at -60, the third guiding line going at 180. Right? This guy guides this. Now you see, why is that? Well, first, for this guy, put in the zeros and the poles. Well, no zeros, but there are 3 poles. One is that, let's just mark them. Yellow maybe, for S, yellow. For S plus 2, you have got this. And then maybe something else, brown for this guy, sure. Right? You put in the poles first. Next, you do no, yes, no, yes. All right? So you got no there, yes there, no there, yes there. Next, starts at a pole. Yes, there is a root locus here, so it has to end at infinity. Goes left. Next, this guy has to start here, has to start here, has to meet at some point and break away. That's called the BAP, breakaway point. And it has to be guided by the asymptotes, right? So comes into the middle, well, not in the middle, not necessarily in the middle, right? Somewhere between 0 and -2. Comes, meets, breaks away, goes here and goes here. And it has to cross the G omega, right? Because it has to be guided by those 2 lines. So it has to go to the right side. This point is called J omega crossing. Why is this important? Stability, right? So we are going to understand with this, at what value of k do we become unstable? As you are increasing it from 0 to infinity, at what value of k did we cross over and we became unstable? So J omega crossing there and as well as here, right? And this guy is my breakaway point, BAP. It doesn't have to be in the middle. May work out to be in the middle for this example, but that's not generally the case. Questions about this example? How do you find number of asymptotes, asymptote angles, asymptote location, and then try to put that up for this particular example? We also need to find a good way of evaluating breakaway point. Now, let me ask you this. Observe only the real axis. Only the real axis, right? Only this, only on the real axis. I'm trying to formulate a strategy about finding breakaway point. What happens on the real axis? Which point has the highest k value? On the real axis, which point has the highest k value? Good. Which is the breakaway point? You guys see that? So the breakaway point is literally the point at which you have the maximum k value as far as the real axis is concerned, right? So this is a mathematical problem now. Differentiate k with respect to x, set it to 0, find the maximum value, right? That will give you what BAP. So we are going to use that exact same strategy to find breakaway point. Differentiate some functions and set it to 0 to find the maximum value. All right, let's do another example here. This is open loop transfer function or loop transfer function is given. You have a 0 at -4, color code it. You have 3 poles. One is at 0, the other is at -2, the other is at -6. Mark them, then you go no, yes, no, yes. All right, let's do that. No, yes, no, yes, no. Next, has to start here and has to be here. So it has to start here and end here, right? And now it has to start here and it has to go inside because there has to be one on the real axis, which means that they come, they meet somewhere between 0 and -2, they break away and are guided by the asymptote lines. What is the asymptote location? Well, find it. Sum the open loop poles minus sum the zeros divided by pole 0 axis. It will work out to be -2. How many lines are there? Same as PZE. So 2 lines. What angles? Pi over 2. So you have 1 line, pi over 2, 1 imaginary line minus pi over 2. Those are going to be the guiding lines for my root locus. So essentially what that means is I have to start here, come, break away, and then be guided by these lines. What I don't know exactly is, do I go this way, or do I go this way, or do I go that way? I don't know that. But I'm going to sketch something that indicates that I have an understanding that it will break away here, and then it will tend towards that. Questions about this example? It's fun, right? Kinda. All right. More fun than convolution. All right. We are not doing too much math. It's just, yeah. All right. Next, center of gravity. So things that whenever, this is sort of a very intuitive concept, right? When you try, there is always a trade-off with things in life in general. When you try to make something more stable, some other thing will become unstable, which is sort of illustrated by poles moving in 2 different directions as you increase k. So you will always have situations where as you are increasing k, if one pole is moving right, the other will move left. But if you have complex conjugates, then you need 2 of them to balance out one real pole. So for example, over here, you see this, you have a root locus where one pole moves right. To balance it out, you have 2 poles that move left, but they are complex conjugate poles. And similarly, if you look at this example, which is another example that we had sketched earlier, one pole moves left. To balance it out, 2 complex conjugate poles move right. So this is for pole 0 axis greater than or equal to 2. If pole 0 axis is greater than or equal to 2, you will see this balancing nature between complex conjugate, between the root locus. How can I use it? Well, sketch out your root locus as an answer. Just check it, right? So this can give you sort of a good insight and a good check whether your answer is going to be correct or not. Next, breakaway points. So breakaway points or break-in points, we will talk about them later. The angles between the entering and exiting loci at breakaway points are equal. So when the root locus break away, they are going to break away or enter at equal angles. So over here, you see you have two poles. One is at 0, the other is at -2. So here and here. Root locus will come together, no, yes, no, yes. So it will come together and it will exit out. And when it exits out, it will exit at equal angles. So the only way to do that with two of them is pi over 2, negative pi over 2. So enters at equal angles and exits at equal angles. Similarly over here, you have a lot of them here. You have one pole at 0, one pole at -2, then you have two complex conjugate poles at -1 plus or minus j. Right? So you have four of them. As you increase, now I have to give you guys a word of caution here. As a starting point, we have not looked at examples where we have complex conjugate poles to start at k equals 0. We have only looked at examples where the k equals 0 corresponds to a pole on the real axis. And that's what we are going to stick with. So our understanding about the root locus is going to be for examples for which k equals 0 corresponds to a pole on the real axis, not on something like this in the complex, because then you have a lot more other angles to worry about, which we are not going to have time to deal with, because things like this, they will sort of exit out at different departure angles, arrival angles, and we don't have time for that. So more rules on top of the already existing ones for those ones. So anyway, let's come back to this example. Here we have four of them entering and exiting. So I have these guys entering on the real axis at equal angles, and they break away to go to their corresponding zeros, or to go to zeros at equal angles. Exit and enter at equal angles. Next, finding the breakaway point, which was again, differentiate things and set them to 0. Let's try to take a look at breakaway points and break-in points. Here, two poles come together, meet, become coincident, break away, come back to the real axis, have a break-in point, and then end at a 0. And we know that. We have seen this particular example. Put the poles in the zeros locations, then do the no, yes, no, yes. Then you know that they have to start at a pole and end at a 0. The only way to accomplish that is they break away and break in on the real axis. Breakaway point is there, break-in point is there. But I don't know whether it is right in the middle or somewhere else. But I do know the range for breakaway and break-in. Breakaway has to be between 0 and -2. Break-in has to be between -3 and -5. And by doing some simple math, I can find those values for breakaway and break-in. Question here, and break-in point has to be between zeros, and breakaway point has to be between poles. And that's sort of very obvious, right? Next, calculating breakaway point and break-in point. In this case, there is only one point, breakaway point. There is no break-in point here. But the strategy is the same. You are trying to find the maximum value of k. So you differentiate k with respect to s and set it to 0. The value of s that makes it possible will be your breakaway point. So what we do is this. Solve for k in the characteristic equation. The characteristic equation is this: 1 plus kg of s h of s is 0. So using the magnitude criteria, you can write k value as -1 divided by g times h. We have seen this before. Now, we have also seen that if you take the derivative of k and set it to 0, then you are tracking the variation of k with respect to s on the real axis, and because you are solving for the real values of s. Take a look at this. These two things. You have a pole here, you have a pole here. These are your starting pole locations when k is 0. And as you so over here k is 0, over here k is 0, right? So if you look at k versus sigma, over here it is 0, over here it is 0 as well, right? 0k here, 0k here, when sigma is 0 and -2. You guys see that? As you're increasing k, this guy, real part is decreasing. This guy, the real part is increasing. So the real part over here is increasing here. and increasing here, right? So this guy is moving. Let's see here. Blue, blue, blue. All right. This guy moves here. This guy moves here. So on the real axis, what are they doing? Moving left, moving right here. As you're increasing k, the sigma value is moving towards BAP, towards BAP. You guys see that? And at breakaway point, you're going to break away from the real axis, which essentially means that k, if you differentiate k with respect to sigma, set it to 0, the value of k that satisfies that is going to give you your breakaway point. So that's what you do. You take k, g of s, h of s, which is this function for that particular example, differentiate k, set it to 0, you get s equals -1. S equals -1 happens to be right in the middle here. So we are breaking away at a point which is right in the middle of the pole locations in this case. So breakaway occurs at s equals -1. Let me actually just, can I find out k value at the breakaway point? So if I know that it breaks away here, breakaway point equals sigma, well, equals -1, say. Can I find the k value at breakaway point? K equals 1 divided by magnitude of h of s, g of s. Evaluate that at s equals -1 at the breakaway point, right? Let me not write -1. I just say breakaway point. That's how I find out what is that k value, right? What is that k value for which you had the breakaway? It will be some value between 0 and infinity. Non-integer, like some finite value between 0 and infinity. Let's see. What about break-in point? Same exact math, but instead of getting two roots, one root here, you will get two roots, right? So here, actually, you see, we got one root here, right? S equals -1. But when you have more points, then you will get two roots for the characteristic for the equation here. When you differentiate, set it to 0, you will get multiple roots. One of them will qualify as a breakaway point, one of them will qualify as a break-in point. And depending on your range, right? For example, over here, 2 poles has to be a breakaway point. If these were zeros, then that would correspond to a break-in point. So let's do that example here. Here we have a different loop transfer function. You have 0 at -4, 0 at -6, a pole at 0, a pole at -2. So we know that we are going to have a breakaway point between here and here, and we are going to have a break-in point between -4 and -6. Apply the same strategy. Differentiate k with respect to s, set it to 0, find the value of s. All right. So here a little bit complex here because of second-order polynomials in the numerator and denominator, but it satisfies pretty quickly actually. So you have k equals -1 divided by g times h. Our g is given, our h is given. Plug those values. Expand, you get a quadratic in the numerator, quadratic in the denominator. Differentiate k with respect to s, set it to 0. So you are using the derivative division property of the derivation. Next, what do you get? You get a quadratic in s based on that. You get two values of s that satisfy that. One of them is going to be -3 plus square root 3, which is -1.26. And the other value is -4.7. Well, we had to break away between these 2 points, so this has to be a breakaway point. And we had to break in between -4 and -6, so this had to be our break-in point, right? So this had to be breakaway, this had to be break-in. And clearly, this is not right in the middle. This so be aware of that it doesn't have to be necessarily right in the middle. Questions about these examples? How do you find so many things, right? Asymptote angles, asymptote location, pole 0 excess, angles at which they exit and enter, where do they exit and enter, what is the value of k corresponding to any point on the root locus, on what criteria we are sketching the root locus. It is based completely on the angle criteria. Let's see, how do you compute break point, break-in point? Final exam, one problem is on this. No points for guessing there. Now, how are you going to practice these problems though? So what I'm going to do is for today and for Monday, no homework that is due, but practice problems will be given and their solutions will be given. So with respect to the root locus, the more number of problems that you are exposed to, I think we have a good set in the examples, but there are other variations of this that you can take a look at in the homework. So I'll give you guys the solution. So maybe you can spend some time for each root locus, try to sketch it by hand, try to compare it with the root locus that I provide in the solutions. Questions, concerns? Fun stuff. Go ahead. Homework? Yeah, so there is one due Monday, but there is no new homework that I'm going to assign. Because if I assign today, I have to make it due on the finals day. So, but then we need some practice for these topics. So practice problems and solutions are the best way to do that. All right. MATLAB has functions to do this too. So if you're curious, let me know, and I think in my solutions, I have the MATLAB code for that as well. Let's see. Now, I was talking about a shortcut to find the stability of the system, right? So this is sort of even simpler than sketching the root locus, because all you have to do is create a RH table. This is called Routh-Hurwitz table. That's what you have. You give me the characteristic equation. I will tell you whether the system is stable or not, irrespective of the order of the polynomial that you give me. So you see this. Let's start with some transfer function, a loop transfer function, right? You're starting with some loop transfer function here. It has some polynomial in the denominator, which will give me the zeros, and it has some polynomial in the numerator will give me the zeros, denominator will give me the poles. So Q of S, the roots of Q of S are the poles. And the long way of doing it would be what? 10th order polynomial, put it in MATLAB, find the roots, observe the location of the roots, the real parts. Real parts of all the roots should be negative, right? So a long way, even longer if you do it on hand, by hand. But there's an easier shortcut way to do it. All you have to do is observe the denominator polynomial. It is a polynomial. So just take a look at write that polynomial out. This is an nth order polynomial. The coefficients are an minus 1, all the way to the constant a sub 0. We are trying to go for the location of the pole. So this is corresponding to Q of S, right? Equals 0. So this is all Q of S. This is the denominator of what? Closed loop transfer function of our system with the feedback. Based on this particular polynomial, we are going to create the Routh-Hurwitz table. How are you going to do that? Well, first fill out the leftmost column, which is simply decreasing powers of S. So S raised to n all the way to S raised to 0. This will essentially give you the first column. Next, you need to fill out rows. The first row will be alternate values of the coefficients. So an minus 2, an minus 4, somewhere from here, and so on. Alternating, starting from the first one. If you don't have a power of S, then it is missing, then it is a 0 there. But you lay out all the coefficients of the denominator polynomial. Next, the second column of this table is all the other remaining coefficients. So you've got in blue, say, this coefficient goes here, this coefficient A3 goes here, and A5 goes here, and so on. So you have got 0, 2, 4, and so on. And then you've got 1, 3, 5, and so on. The first two rows of this table are like 3 seconds work, right? Like you just read off the polynomial. Next. These coefficients are actually computed based on the determinant of the other matrices. We'll try to take a look at that. Bn minus 1, this guy is this guy is actually computed using this equation right here, which is -1 divided by an minus 1. So this is -1 divided by an minus 1, and the matrix of a 2 by 2, a determinant of a 2 by 2 matrix. What is that? Let's see. An right here, an minus 2 right here, an minus 1 right here, an minus 3 right here. So let me just, instead of having all of these red lines, let me just box it up. These are all going to be 2 by 2 matrices. Irrespective of how many values you have over here, they're all going to be 2 by 2s. So Bn minus 1 is take the one value an minus 1 there, -1 divided by that, and then determinant of the 2 by 2 submatrix, which is this guy. Similarly, Bn minus 3 is what? -1 divided by an minus 1, and then you have an minus 4, an minus 1, an minus 5. So for this guy, you have this, and this. Determinant of that. So you just sort of erase that, remove that. You guys see that? That will fill out your next column. After that, you have C's. You only need to do that until you stop getting zeros, right? Like once you go further out in the A's, B's, C's, you will eventually start getting zeros. You don't have to go any further down. Next, you have C's. For getting Cn minus 1, you do -1 divided by Bn minus 1, and then the determinant of this guy right here. You guys see that? So just applying some determinant. You guys remember the determinant of 2 by 2 matrix, right? Also there on the slide later on. But it's just determinants of 2 by 2 matrices. First two columns are right off the polynomial. After that, you're just evaluating determinants. Also have to be careful with this, -1 divided by the coefficients there. Fill out the matrix as long as you're not getting zeros repeatedly. Then we are going to observe the table. So once you have the Routh-Hurwitz table filled in with numbers, maybe they are all numbers, maybe they are parameters, like k might start appearing here if you have those polynomials in k. But if you want to comment about the stability of the system, then the statement is it. Stability if and only if there is no sign change in the first column. So all you would have to do is observe the first column of the Routh-Hurwitz table. If there is no sign change, they all are positive or they all are negative, then the system is stable. That's it. All you have to do is first find this. Look at the sign changes in that. Good. Oh, no. So here you see this guy will start depending on this guy and the determinant of these, right? So this one is also involved in that. So you would have to actually go out to sort of all the non-zero ones, because then if this guy depends on this, then this guy will depend on this, right? So you would have to actually go. So until you start getting zero here, you would have to actually keep going down. All right, go ahead. So the first rule is stability if and only if there is no change in the first, no sign change in the first column. All the numbers in the first column are all positive or all negative. Then the system is stable. In fact, the number of sign changes are actually going to tell you the number of poles in the right half plane. So if you have one sign change, say half of them are positive, half of them are negative in the first column, then that means that you have one pole in the right half plane. Number of sign changes is actually going to tell you the number of poles in the right half. Next, let's see. I think we have stated the motivation pretty clearly. Instead of finding 100 roots and determining whether all the roots are in the left half or not, you just try to take a look at one column in the Routh-Hurwitz table, and you know the solution to this. Let's see it. All right, so we have what we are doing over here is we are setting up our polynomial such that the first coefficient is always greater than 0, which essentially means if it is not less than, if it is negative, you just multiply the entire equation by -1 and make it positive, right? It's pretty easy to manipulate that. Once you manipulate that, put it in. So you have got the coefficients, every other one, and all the ones that are remaining. Then you have computed bn-1, cn-1 using the 2 by 2 determinants and the formulas that we talked about. Once you construct the Routh-Hurwitz table, then you start looking at the sign changes in the first column. No sign changes in the first column. Well, we started with an to be greater than 0, right? So no sign changes means everything in the first column has to be positive. If everything in the first column is positive, then we can say that the system is stable. So count the sign changes in the first column. We are looking for all of them to be greater than 0, right? If an is 0 and all of them has to have the same sign, all AKs have to be greater than zeros, and everything over here has to be greater than 0. So essentially, this is saying, let's see, AK has to be greater than 0. What does that mean? That means each of these values has to be greater than 0. Next, what does this mean? First column entries have to be greater than 0. That means these guys have to be greater than 0. So look at all the coefficients of the polynomial. They all should be greater than 0. And all the first column entries should be greater than 0. And we'll take a look at some examples where we will show that if this has to be met, then this will be true. And like I also said, if there is a sign change, then the number of sign changes in the first column will actually tell me the number of poles in the right half. So if half of them are positive, half of them are negative, there's one pole in the right half plane, making the system unstable. Next. All right, so we are starting simple here. Polynomial, find the first row. So for the first row, you have this guy, and so on. So you have those. And then for the second row, you have every other one. So you have those. Once you find the first two rows, then you start using the determinant of the matrix. Determinant of the 2 by 2 matrix is AB minus CD. Hold on, right. AB minus CD. Yeah. Next, using this particular formula, which is -1 divided by an minus 1 to find bn minus 1, determinant of this particular matrix is right here. We have already filled out the first row using the polynomial. Next, we start filling out bn minus 1. Once we find bn minus 1, then you move on to bn minus 3, which is the determinant of this and this over here, with -1 over a minus 1 remains as is. Then you fill out the third row, n minus 1, n minus 2 row. Then you go even further down. When you go even further down, let's just try to write Cn minus 1 here. When you are using Cn minus 1, what are you doing for that? You're doing -1 divided by Bn minus 1, and then you're finding the determinant of this matrix, right? An minus 1, an minus 3, bn minus 1, bn minus 3. And then you just keep filling out all the rows until you get all zeros. Yeah, that formula is written over here. Cn minus 1, I just wrote that. And then you're writing it again. Continue this pattern. You require all the elements in the first column to be non-zero, and we'll come back to that. Let's see. Let's try to do it for some example polynomials. We'll start simple, and then we'll try to increase the order of the polynomial here. The order of your polynomial over here is a second order polynomial. This is what? This is the denominator of the closed loop transfer function, or for that matter, any transfer function. What are the first row? A2, A0, that's it, right? There are only two of them. In the next one, I have A1, nothing, A1, 0. I only need to find B1. What is B1? B1 will be equal to A0 in this case. Why? B1 equals -1 divided by A1, and then determinant of, what is that? A2 times 0, that's 0, minus A0 times A1, right? A1 will cancel out, you will be left with just A0. So B1 is A0. So you see, if all of these things have to be greater than 0, and if each of them has to be greater than 0, A2 has to be greater than 0, A1 has to be greater than 0, A0 has to be greater than 0. Then you have all of those coefficients going to 0, and there is no sign change in the first column. So stability if all three denominator coefficients have the same sign. If it is all positive, that works. If it is all negative, you just multiply by -1. You try to set your A2 to be greater than 0. Questions about this example? All right, let's try to increase the polynomial coefficient here. 3. What do you have for 3? Again, first two columns are going to be straightforward. 3, 1, that's it. And then you have 2 and A0 there and there. Then using the formula that we talked about, you find B1. Actually, this guy will be 0, because once you go for this, you're using this guy with 2 zeros. Well, because of those 2 zeros, the determinant will go to 0, and you don't have to include this. B1 will have what? -1 divided by A2 multiplied by the determinant of A3, A1, A2, A0, which is right here. And you can simplify this. Similarly, you can find out C1. C1 will come out to be A sub 0. Next, you want two things to happen here. What are they? One, A3 greater than 0, A1, sorry, A3, A2, A1, A0 should all be greater than 0. What is the second thing? Second thing is A3 greater than 0, A2 greater than 0, B1 greater than 0, C1 greater than 0. No sign change with A3 to be greater than 0 means all of them has to be greater than 0. You have already found out B1 and is C1. If you look at which one is this? B1, what is B1 going to give us? You see this? This gives me -1 divided by A2 multiplied by A3, A0 minus A2, A1, right? Or I can simplify this to be A3, or I can say A2, A1 minus A3, A0 divided by A2. So if B1 has to be greater than 0, if B1 has to be greater than 0, A2, A1 has to be greater than A3, A0. Is written up over here. Now, if we know that A3 is greater than 0, C1 is greater than 0, right? A3 is greater than 0, A0 is greater than 0. That means that this guy has to be greater than 0 as well, which implies A1 has to be greater than 0. So all the coefficients here are again greater than 0 for stability to happen, A3, A2, A1, A0. Because B1 is related to A3, A2, A1, A0, and C1 is in fact directly A0. Just using simple construction of the table, there are patterns, you are using determinants, observing sign changes. Next. Now, let's take, this is our last example here. Let me go through this very quickly. This one is, what is the root locus? How do you find the J omega crossing? The J omega crossing is essentially finding the K value as the root locus crosses the J omega axis. The long way of doing it is what? Is by looking at corresponding S, you plug that into the magnitude criteria, find the value of K. The other way of doing it is by setting up an auxiliary equation using the Routh-Hurwitz criteria. Let me take a look at that with an example. We are trying to use that shortcut, Routh array or Routh-Hurwitz criteria. We have a loop transfer function that is given to us. Using that loop transfer function, we can sketch out the root locus based on the rules that we have already talked about. We know that at some point it will cross the J omega axis because of asymptotes and center of gravity and all of those rules. We want to find out where is this point, J omega crossing, and what is the value of K. To set that up, we are going to look at the characteristic equation over here of the denominator. This is the denominator of the closed loop transfer function, 1 plus k g of s h of s. Set it to 0. What do you get? You get a cubic in S for this particular example. Put these values in the Routh array. You are going to get this: s cubed, s squared, s1, s0. You get 1 and 2 for this and this. You get 1 and 2. And for this and this, you get 3 and what? K. 3 and k. Then the next value will be what? It will be, the way you're getting this is essentially -1 divided by 3, 1, 2, 3, and k, right? Simplify that, you get this, 6 minus k divided by 3. And then the last value, similarly, you can do, the same equation as before, you get, simplify that to k. Now, if that's, what you're going to do is take the linear function for that and set it to 0. When you take the linear function, which is corresponding to s to the 1, you set it to 0, that is going to be the value of k for which you cross the g omega axis. So that can help you sort of, when k is 6, what is the value of s? Well, you can use the root locus to give you that. When k is 6, right, the equation over here is going to be 3s squared plus k times s raised to 0, right here, for s squared. With k equals 6, substitute that, you will see that the value of s is plus or minus j square root 2. So this is, you can use this to find out where it crosses the g omega axis and what is the value of k corresponding to that. All right, let me stop over here. Let me stop recording. Thank you for bearing with me for the additional time here. I will see you guys on Monday.